Hello everyone, welcome to my channel. This is Rekha Venkateshwarlu. In the present class, now I am going to discuss the topic Lissajous figures, combinations of two mutually perpendicular simple harmonic motions of same frequencies. This is the part of syllabus of the BSc Physics first year, first semester, that is Mechanics and Oscillations, Unit 4. The contents of the present lectures that we are going to discuss in this present class are the linear combination of simple harmonic motions of same angular frequency. Then after we will define what are the Lissajous figures, and then after we will discuss the topic combination of two mutually perpendicular simple harmonic motions of same frequencies. At the end of class, we will see the conclusions. Yes, we know that the displacement of simple harmonic motion x is equal to a sine of omega t plus phi or a cos of omega t plus phi, right? So here we discuss the case when more than two simple harmonic motions, whether having the same direction or in perpendicular directions, if they are superimposed, what would be the resultant? Okay, so here the topic we are going to discuss is the resultant motion of two simple harmonic motions. Two simple harmonic motions, particularly when they are acting at perpendicular directions. At mutually perpendicular directions, the combination of two simple harmonic motions. So that is we are going to discuss here, sir. So here, if x1, x2, x3, and so on, xn are the displacement of individual superimposed waves, then the displacement of the resultant wave is given by x is equal to x1 plus x2 plus x3, so on, xn. So this is called the principle of superposition. Principle of superposition. Okay. When more than two simple harmonic motions or more than two waves traveling in the same direction, then their individual displacements are x1, x2, x3, and so on, xn. If they superimpose, that is nothing but if they combine with each other, then the displacement of the resultant wave is given by x is equal to the vector sum of their individual displacement, x1 bar plus x2 bar plus x3 bar and so on. Suppose if these waves are traveling in the same direction, then the magnitude of the resultant wave displacement equal to simply the algebraic sum of their individual displacements, x1 plus x2 plus x3 and so on, xn. This is called the principle of superposition. The principle of superposition. So let me repeat. When more than two waves or two simple harmonic motions are superimposed with each other and their individual displacements are x1, x2, x3 and so on, xn, right? Then the resultant displacement of that resultant wave is equal to x is given by the sum of their individual displacement. So mathematically we express it as x is equal to x1 plus x2 plus x3 and so on, xn. Okay, sir. So, so here we will discuss the Lissajous figures. What is meant by Lissajous figures? Then after we will discuss the case, the combination of two mutually perpendicular simple harmonic motions. Right, sir? So first, let us define what are the Lissajous figures, sir. What are the Lissajous figures? Right. When two simple harmonic motions, when two simple harmonic motions acting perpendicular direction of same frequency or different frequency are superimposed, then the combination or the resultant motion would be a curve. Those curves are called Lissajous figures. Those curves are called Lissajous figures. So the definition of simple harmonic, Lissajous figures is given by, so So what is the definition of Lissajous figures? That is when a particle is I'm typing here, when a particle is subjected to mutually subjected to simple harmonic vibrations, to simple harmonic vibrations, okay, simple harmonic vibrations of of unequal frequencies, unequal frequencies simultaneously simultaneously at right angles to each other, at right angles to each other, the resultant motion of the particle, the resultant motion of the particle traces a curve, traces a curve, traces a curve. These curves are called Lissajous figures. These curves are called Lissajous figures. Okay, that's it. So what I'm saying is the resultant motion of a particle subjected to simple harmonic vibrations of unequal frequencies simultaneously, which are acting at right angles, then the resultant motion of the particle will trace a curve. Thus curves are called as Lissajous figures. అంటే ఒక పార్టికల్ మీద సైమల్టేనియస్ గా పర్పెండిక్యులర్ డైరెక్షన్ లో టూ సింపుల్ హార్మోనిక్ మోషన్స్ యాక్ట్ అవుతున్నప్పుడు పార్టికల్ యొక్క రిజల్టెంట్ మోషన్ కర్వ్ పాత్ అవుతుంది. సో అటువంటి కర్వ్స్ ని లెసాజిస్ ఫిగర్స్ అంటాం సార్. ఇక్కడ సో మనం డిస్కస్ చేయబోయే టాపిక్ ఏంటంటే కాంబినేషన్ ఆఫ్ టూ సింపుల్ హార్మోనిక్ మోషన్స్ ఆఫ్ సేమ్ ఫ్రీక్వెన్సీ, దట్ ఈస్ ఇన్ ద ఫ్రీక్వెన్సీ రేషియో 1:1. Two simple harmonic motions are acting on the particle at a right angles, so which frequencies are in the ratio 1:1. Okay, so equal frequencies, unequal frequencies, there are two cases, but here only we restrict our discussion for equal frequencies, sir. Right, so let us see what is that. We know what is the displacement equation. X is equal to a cos omega t plus phi. If initial phase is equal to 0, that is the phase at t equal to 0, phase is equal to 0 at the time t equal to 0 second, then we write the equation x is equal to a cos omega t. So displacement equation of simple harmonic motion, we know x is equal to capital A cos of omega t, where capital A represents amplitude, omega angular frequency. So general expression we know A cos of omega t plus phi, where phi is the initial phase or phase constant. If initial phase of the particle is 0, that is phi equal to 0 substituted here, then the expression becomes x is equal to capital A cos omega t. Right, sir? So another equation I am taking, the second equation, the second simple harmonic motion, which is acting along the y direction, that is y equal to capital B cos of omega t plus phi. X is equal to A cos omega t is the simple harmonic motion along x axis. The simple harmonic motion acting along the y axis is represented by y is equal to b cos of omega t plus phi. In this expression, what is b? B is its amplitude. B is amplitude. Again, omega, angular frequency, and phi is initial phase or phase constant. So if you observe these two equations, x is equal to e cos omega t is equation 1, y is equal to b cos of omega t plus phi, another equation. Okay, the first equation is, represents what? This is the simple harmonic motion executing along the x-axis. This is the simple harmonic motion lies along the y-axis. Here, what is the phase at the time t? Omega t. So, what is the phase of the second motion at the time t? Omega t plus phi. So, what is the phase difference between these two simple harmonic motion? Omega t plus phi minus omega t, that is phi. Okay, it is very clear if you observe the equations here, the phase at any instant of time omega t for the simple harmonic motion along y-axis, the phase omega t plus phi. Therefore, here the phase difference between these two motions is phi. Okay, sir. A and B represents amplitudes respectively. Omega is angular frequency. So from the equation, the first equation, you write cos omega t as the subject. So what is cos omega t? Cos omega t is equal to x by a. So from this, sine square omega t equal to 1 minus cos square omega t, right? So 1 minus cos square omega t is, you will get 1 minus x square by a square, sir. 1 minus x square by a square. Okay. From the second equation, okay. From the second equation, what is the second equation? Y is equal to capital B cos of omega t plus phi. From that, you write omega by b is equal cos of omega t plus phi. Right, sir? So right hand side, you have cos of a plus b form. Cos a plus b formula, cos a cos b minus sin a sin b. Okay. So by using that, let us expand the right hand side term, cos omega t cos phi minus sin omega t sin phi. Okay. Y by capital B equal to, right side we got cos omega t cos phi minus sin omega t sin phi. But already we have cos omega t equal to x by a, right? Sin omega t equal to under root 1 minus x square by a square. So let us substitute cos omega t sin omega t values. Okay, cos omega t sin omega t values in this third equation. So then you will get y by b is equal to cos omega t x by a cos phi written as it is minus sin omega t 1 minus x square by a square whole power of sin phi. Okay, sir. Then you write 1 minus x square by a square whole power of sin phi as a subject. Then x by e cos phi minus y by b. So squaring both sides, you will get left side what you will get 1 minus x square by a square whole power of whole square, that is 1 minus x square by a square sin phi whole square sin square phi, that equal to right side you will get a minus b whole square form. So expansion a square plus b square minus 2ab. According to that, x by a cos phi whole square, you will get the first term x square by a square cos square phi plus y square by b square minus 2xy by ab cos phi. Okay, sir. From this sine square phi, okay, sine square phi, expanding this sine square phi minus x square by a square sine square phi, right side, is equal to right side x square by a square cos square phi plus y square by b square minus 2xy by ab cos phi. Bring this x square by a square term to the right side. Then by taking x square by a square common, cos square plus sin square phi plus y square by b square minus 2xy by ab cos phi equal to sin square phi. But cos square plus sin square phi equal to 1, then this equation becomes x square by a square plus y square by b square minus 2xy by ab cos phi equal to sin square phi. So whatever the equation we got now, so final equation, so what is that? The final equation we got here, x square by a square plus y square by b square minus 2xy by ab cos phi equals sin square phi. This equation represents the resultant motion of the particle which is subjected to mutually perpendicular simple harmonic motions of different amplitudes. Already we started our discussion that the one simple harmonic motion is along x-axis with amplitude e. Another simple harmonic motion is along y-axis of amplitude b. Then the resultant motion of the particle x square by a square plus y square by b square minus 2xy by ab cos phi equals sin square phi. So this equation represents the resultant equation of motion of that particle. Right, sir? So this equation represents an oblique ellipse. This equation represents an oblique ellipse along the coordinate axis. Okay, along the coordinate axis. Here, let us see some cases, sir. So, here, this resultant equation, the resultant motion of the particle depends on amplitudes, amplitudes of the individual simple harmonic motions, and angular frequency and phase difference. So these three factors decide the resultant motion of the particle. Right, sir? If you observe the equation, it's very clear. A, amplitude of the first simple harmonic motion. B, amplitude of the second simple harmonic motion. Phi is the phase difference. Phi is the phase difference. So in our discussion, we considered the same frequency. If they are different frequency, that is also deciding factor. That is also one of the deciding factor. Right. Let us see the cases. First, the phase difference between two mutually perpendicular simple harmonic motion phi is equal to 0 or 2 pi. The phase difference is 0 or 2 pi. What happens? Then sin phi equal to 0, cos phi is equal to 1, you know. If phi is equal to pi, then also sin 2 phi 0, cos 2 phi equal to 1. So for the phase difference, phi is equal to 0 or 2 pi radians, that is nothing but 360 degree. Since sin phi equal to 0, cos phi equal to 1, substituting these two values in this equation, that is what x square by a square plus y square by b square minus 2xy by ab cos phi equals sin square phi. So దాంట్లో substitute చేస్తే then you will get x square by a square plus y square by b square minus 2xy uh, minus 2xy by ab is equal to right side 0. Right side will get 0. So left side you can write it as x by a minus y by b whole square equal to 0, because it is in the form a minus b whole square. X by a minus y by b whole square equal to 0. So from that, x by a minus y by b equal to 0. So from that, y is equal to b by a into x. So it has the form y is equal to mx. So the equation what we got has the form y is equal to mx. So y is equal to mx is a straight line passing through origin. So it is very clear that the resultant motion of the particle when the phase difference is equal to 0. So what type of two simple harmonic motion? When the particle is subjected to mutually perpendicular simple harmonic motions of different amplitudes and having the phase difference 0 or 2 pi radian, then we got the resultant equation as a straight line. So that is the resultant motion of the particle y is equal to b by a into x, and you will get the straight line passing through origin. So this is also called as in optically linearly polarized. Linearly polarized and resultant motion along the straight line untundanamata. Okay na. So that would be here this will indicate the vibrations made by a particle along the diagonal of a rectangle. Along the diagonal of a rectangle. Right, sir. Now, the second case, when the phase difference phi is equal to pi, then substituting that here, you will get y is equal minus b by a into x. When phi is equal to pi, sin phi is equal to 0, cos phi equal to minus 1. You substitute that values here. Cos phi is equal to minus 1, sin phi equal to 0. Right side you will get 0. Left side you will get here plus. x square by a square plus y square by b square plus 2xy by ab cos 2xy by ab equal to 0. So left side you can write it as x by a plus y by b whole square equal to 0. Then uh, we'll get y is equal minus b by a into x. Okay. For the phase difference, phi is equal to 180 degrees or pi radians, then the resultant equation y is equal minus capital B by capital A into x. It is also y is equal mx form, but here slope is negative. Therefore, the path of the particle will be along the second diagonal of the rectangle. So, if you take the rectangle, I am drawing here. Here, the one particle is along the x-axis, another particle is vibrating the simple harmonic motion along the y-axis. Right, sir? Along the y-axis. Okay, along the y-axis. Here, amplitude is capital E. Along the y-axis, the amplitude is capital B. For phi is equal to 0, for pi equal to 0 or 2 pi, then the resultant motion is one diagonal of this rectangle. One diagonal of this rectangle, sir. Okay. So here you can show the directions. The resultant motion along the straight line. Along the straight line like this, that will be repeated. The direction of particle will be along the straight line. That is along the diagonal of rectangle. So for the second case, when phi is equal to pi, when phi is equal to 180 degree or phi, then the resultant motion is also a straight line, but this is the second diagonal of this rectangle, second diagonal of this rectangle. So here the direction of particle motion will be along this straight line. Okay, I hope you understand. When the phase difference phi equal to 0 or 2 pi, then the resultant motion would be along the straight line. So here it is linearly polarized. When phi is equal to 180 degree, then the resultant motion would be along the straight line. It is also linearly polarized. Okay, sir. Now, second case is third case, when the phase difference is equal to pi by 2 or 90 degrees. Then sine pi by 2 equal to 1, cos phi equal to 0. Substituting that in this equation, resultant equation, x square by a square plus y square by b square minus 2xy by ab into 0. So the third term becomes 0, equal to right side sine square pi by 2 1. Then x square by a square plus y square by b square equal to 1. So the resultant equation you will get x square by a square plus y square by b square equal to 1. So what it represents, sir? X square by a square plus y square by b square equal to 1 represents what? It is ellipse equation. Therefore, when the phase difference is 90 degree, when the phase difference between two mutually perpendicular simple harmonic motions of different frequencies, different amplitudes and same frequency, the resultant motion would be ellipse for the phase difference phi is equal 90 degree. In this, if their amplitudes are equal, A is equal to B, substitute a 7 you will get x square plus x square by a square plus y square by a square equal to a square. Then x square plus y square equal to a square. But x square plus y square equal to a square represents what? Circle. But the resultant motion of the particle would be circular motion. Okay, the resultant motion of the particle is a circle or circular path. X square by, that is called circular polarized. This is called elliptically polarized. When you get the ellipse equation, that is nothing but elliptically polarized. If you get the circle equation, x square plus y square equal a square, that is called as circularly polarized. Okay, so for the phase difference 90 degree, for different amplitudes, you will get ellipse equation. For same amplitude and same frequency, we will get x square plus y square equal to a square. Next case, when the phase difference is 3 pi by 4. 3 pi by 4. Then cos pi by 4 what? Cos pi plus pi by 4. You can write cos pi minus pi by 4. Right? So you will get what's that? Cos pi minus pi by 4. That is sin pi by 4. Sin 3 pi by 4. Sin pi minus pi by 4 minus sin pi by 4 minus 1 by root 2. So cos pi by 4 equal to 1 by root 2, cos 45. Sin 3 pi by 4 equal minus sin pi by 4, you will get minus 1 by root 2. So same, you substitute these two values in the resultant equation. This is x square by a square plus y square by b square. In this equation, you substitute cos phi and sin phi value. Cos phi equal to 1 by root 2 substitute. Sin phi equal to minus 1 by root 2 substitute. Then you will get the resultant equation, that is this one, oblique ellipse. Then you will get oblique ellipse. For phi is equal to pi by 4 phase difference, you will get the oblique ellipse like this. So that lies in the first and third quadrant. First and third quadrant. For the phase difference, phi is equal to 3 pi by 4. Here also you are getting the oblique ellipse, but it is in the second and fourth quadrant. Okay, second and fourth quadrant. Here the ellipse is what? Here you observe ellipse is in this direction, clockwise direction. Here the ellipse, oblique ellipse is what? Here this is in anti-clockwise direction. Okay, so let me repeat. You observe these figures, sir. For the phase difference, phi is equal to 0 or 2 pi. This is along the diagonal of rectangle, right? So resultant motion of the particle would be along the straight line. When the phase difference phi is equal to pi by 4, you will get oblique ellipse, that is that lies in the first and third quadrant along this direction. This is in anti-clockwise direction, clockwise direction. So clockwise direction ellipse, you will get the resultant equation, a resultant motion of the particle. For the phase difference phi is equal to pi by 2, it is ellipse. It is ellipse, right? Like this. For phi by 2 like this. For the phase difference phi is equal to pi by 2 clockwise direction. If you take pi is equal to 3 pi by 2, then you will get the ellipse equation in anti-clockwise direction. If amplitudes are same, this would be the circle. This would be the circle. So therefore, that would be the circle. So that you can imagine the circle in this rectangle. For the phase difference between two simple harmonic motion is 3 pi by 4. Then also you will get the same oblique ellipse, but it is in the second and fourth quadrant. It is in anti-clockwise direction. Okay, sir. You observe the flashlight. For the phase difference, phi is equal to pi, that is 180 degree. Here, it is also linearly polarized, but it is the second diagonal of the rectangle. Okay, we have the two diagonals. This is one diagonal, it is another diagonal. For the phase difference 0 or 2 pi, we are getting the resultant motion along this diagonal. For the phase difference 180 degree, the resultant motion is along this is slope negative, along the second diagonal of the resultant motion. These figures are called Lissajous figures. These figures are called Lissajous figures. So that is the resultant motion. The cause are the resultant paths of a particle subjected to mutually perpendicular simple harmonic motions of different amplitude for the different phase difference. We are getting the different resultant motion, that may be straight line or ellipse, ellipse again, oblique ellipse or symmetric ellipse, circle, whatever it is. These figures are called Lissajous figures. Okay, if you take the different frequency simple harmonic motion acting in perpendicular direction, then obviously all these figures you will get the cause. Those curves are called Lissajous figures. Okay, so in this present class, what we discussed is first the principle of superposition of two waves or superposition of two simple harmonic motion. That is nothing but when the particle is subjected to when the particle is subjected to more than two simple harmonic motion, or when more than two simple harmonic motions are superimposed, then the resultant displacement of the particle equal to the algebraic sum of their individual displacement, right? This is called principle of superposition. Then after we define Lissajous figures, there we discuss the case, the combination of two simple harmonic motions with the same frequency moving in perpendicular direction. So there, how we approached, first we considered two simple harmonic motions. One is executing along x-axis, that is represented as x is equal to a cos omega t. Another simple harmonic motion executing along y-axis, represented as y equal b cos of omega t plus phi. Here A, amplitude omega angular frequency. In the second equation B, amplitude omega angular frequency phi initial phase. The phase difference between these two is phi. So then from the first equation cos omega t equal x by a. From that you write sin omega t, right? Next you consider the second equation. From that you write y by b equal cos of omega t plus phi. So right hand side, you expand that cos omega t cos phi minus sin omega t sin phi minus sin omega t sin phi. Okay. Uh, so then y by b equal to substituting cos omega t sin omega t values, that is x by a cos phi minus 1 minus x square by a square whole power of sin phi. From that, again the second term written as a subject, you got this equation. Squaring both sides, 1 minus x square by a square sin square phi equal to x square by a square cos square phi plus y square by b square minus 2xy by ab cos phi. Again left side expanded. So on simplification, finally we got this equation. What is that? X square by a square plus y square by b square minus 2xy by ab cos phi equals is sin square phi. So this equation represents oblique ellipse. Okay, the resultant equation of motion. This is the resultant equation of motion, or the equation of the resultant motion of the two, the combination of two mutually perpendicular simple harmonic motion. Right, sir. So here, the resultant path of the particle, the path followed by the particle depends on phase difference. The phase difference cases that may be 0 or 2 pi, that may be pi by 4 or 3 by 5 or pi by 2. So for different phase difference, here we have seen. For the phase difference phi equal to 0 to pi, then sin phi equal to 0, cos phi equal to 1. Then we got the equation y equal to b by a to x. So this is a straight line. So therefore, uh, the resultant motion of the particle is a straight line that is along the diagonal of one rectangle. When the phase difference phi is equal to 180 degree, then we got y equal to minus b by a into x. This is also straight line. Of course, it is the second diagonal of the rectangle. For the phase difference phi equal to pi by 2, that is 90 degrees, we got the ellipse equation, x square by a square plus y square by b square equal to 1. Right, sir? For the phase difference phi equal pi by 2 and their amplitudes are same. Okay, if a equal to b and phase difference 90 degrees, then the equation becomes as x square plus y square equal to a square. This is circle equation. Okay, so the Lissajous figure is a circle. Here the Lissajous figure is what? Ellipse. For the phase difference pi by 4 or 3 pi by 4, you will get the oblique ellipse. For phase difference pi by 4, you will get this clockwise ellipse lies in the first and third quadrant. For the phase difference 3 pi by 4, same we got the oblique ellipse in anti-clockwise direction lies in the second and fourth quadrant. Right, sir? So this is a very important question, so that you have to practice more the derivation and don't confuse with these phase differences. So for different phase differences, simply we are substituting the values of cos phi, sin phi values in